Hello dear colleagues, my name is Pavel and I am a sales manager at Passatinnovations. Thanks for your attention and time. This is the second webinar concerning our vibration and temperature sensor VTS3D as a part of condition monitoring system of industrial equipment. This webinar will be more practically orientated. We will answer the questions how to connect and how to work with our sensor, how to work and where you can find our free software. With the first webinar you can find on our website and YouTube channel. So today I'm with my colleague Vladislav Savenia, and Vladislav, please start.
Hello to everybody. Today I will show you VTS 3D capabilities in action. I will conduct a series of tests on our vibration test system, and also I want to show you some scenarios for connecting to a PC. Firstly, let's take a look at the package. Here by default we have our sensor and mounting plate for a screw. Additionally, you can order magnetic mounting plate, and also because VTS 3DM comes with the Modbus RTU provided by RS485, you may need some converter to a USB or other port type, and we have designed our own RS485 to USB converter with power delivery that very nice complies with our sensor. You could order it in near future, I hope. So right now I will say a couple of words about our today's equipment. Today I'm gonna use Tira TV51110 vibration exciter. As a control system for it, we have Z24 made by the Lab company. As a feedback acceleration sensor, we will use BC111. Also, our vibration exciter stands on calibrated stand, and vibration exciter is calibrated too with these two handles. Everything is calibrated with level gauge. To connect VTS 3D to a PC, we've created RS485 to USB converter. This one is a prototype, shame on us. We've designed a beautiful and convenient body, so in near future it will be available at our website to order. We want to be sure that you can set up our device very easily. Also, this device has power delivery feature, so another way to use this device is to drag this device, sensor and a notebook as a mobile vibration monitoring kit. So another way to connect our device to PC is to use a gateway. We've created this stand to show you the real example about how to do it. Here you can see power supply unit. Also there is a Modbus RTU to Modbus TCP gateway, and here we've placed a couple of terminals to connect wires between these devices to make it more like convenient way. So all you need to do after that is to put your two power wires into these terminals and put two interface wires A and B in other terminals that are connected with interface pins of this gateway. After that, on the output of gateway, you can easily connect our sensor to a PC via Ethernet cable. And of course, our service software for VTS 3D supports this feature. You can not only choose Modbus RTU protocol, but also you can choose Modbus TCP protocol. All you need to do is to put your IP address of gateway, server port, and Modbus ID of the sensor. So after that, press connect and magic. So let's continue our conversation. I suggest to start our conversation from the product page. To do so, you need to visit our website, click on products, then vibration diagnostic systems, vibration temperature sensor. Okay, so here we have like a short of description about our sensor, about its capabilities. And here also you can find a button to download our service software. I will not do this to save our time because I already have downloaded it. And also here you can see a button for a datasheet. Okay, let's move on to installation process of our service software. It is very easy to install. All you need to do is to press maybe 2 or 3 times button next, install. Okay. Okay, it suggests to launch VTS. Okay, agree. Here we can see the connection page where you can choose Modbus protocol. Our software supports 2 protocols. It is Modbus RTU and Modbus TCP. To connect via Modbus TCP, you need to set your IP address of your gateway, your port number, and Modbus ID of VTS 3D sensor. I will choose Modbus RTU because my sensor is connected via COM port, via USB converter. Here you need to choose COM port. Also we need to fill these connection fields. In my case it is first ID, 115 and 200 bit per second, non-parity, one-stop bit. Okay, press connect button. Okay, maybe I'm wrong and device not found. Okay, something went wrong. Here on the home page we have our standard vibration characteristics. As you can see, here we have RMS acceleration values for 3-axis, RMS velocity value for 3-axis to RMS displacement values, high frequency characteristic. High frequency means the frequency with the highest energy in this spectrum, in sensor spectrum. peak-to-peak value, and peak factor value. So these three values, characteristics, acceleration, velocity, and displacements, are represents like the standard frequency bands, as it says in datasheet. For acceleration from 10 to 3 kilohertz, for velocity from 10 hertz to 1 kilohertz, and for displacement from 10 to 200 hertz. What is frequency band in our meaning? Frequency bands are given at -3 decibels, which corresponds to a conversion factor 0.707 of the nominal value at a calibration frequency at 80 Hz. So we have to put some filters that described in this standard ISO 2954, because it is required if you want to your product be like a measurement unit, like a verified measurement unit. You need to comply with these frequency filters. And here we have a graphical description of this filter. So for acceleration we have -3 decibels at 10 and at 300 hertz, 3000 hertz. For velocity we have -3 decibels at 10 and 1 kilohertz. And for displacement we have -3 decibels at 10 and at 200 hertz. So we will see it in action. I will put some magnitude on our vibration exciter. Firstly, I will put it at calibration frequency 80 Hz, and to see the difference compared to this calibration frequency, after I will put 10 Hz, and from lowest to the highest I will put 200 Hz, 1 kilohertz and 3 kilohertz. Okay. So let's start from 80 Hz. 80 Hz. I will put 2G. Okay, start. So in this window we have measurements from our feedback sensor BC111, and here the measurements of our sensor. Okay, so let's compare the values of our sensor to feedback sensor. As we can see, at calibration level there are no any like filters applied on this frequency, so we are getting the values as it is, and you can see that the values almost the same compared to feedback sensor, almost the same. Okay, let's change our frequency to 10 Hz to see the difference. Okay. Here I have put 2G magnitude, because if I put let's say 3G, our program says that we are out of our limits of our vibration exciter, so it has 6.5 displacement limit. So because due to that I will put 2G as at 80 Hz. Okay, so let's see what happens. Okay, our sensor has its level, almost has its level. Okay, we are on the level. And our feedback sensor right now has 14 meters per second RMS for vibration acceleration, but our sensor says that it is 10. So as it says in the datasheet, at our frequency limits, we have conversion factor 0.707. Let's check it. I have a calculator here. So if I multiply this value by 707, so we have like very close measurements, maybe 2% of error. In the same way, we can recalculate this value to see the filter in action. We need to multiply it by 0.707. So I want to say that at these frequencies we have some leverage, about 3 decibels, and this is not an error. I want you to understand this because if you can, as you can see, our sensor has almost the same measurement if we apply the filter coefficient. And the last one is displacement. Like almost the same. Almost the same. You can calculate the error percentage by itself. And as you can see, our sensor says that the frequency with the highest energy is 9 Hertz. We are having 10 on our vibration exciter. Let's also see this peak to peak. Peak to peak is magnitude characteristics, so we need to calculate our 2G and then multiply it by 2. Okay, 3924. A little error we have here, and let's move on to 200 Hertz. So 200 Hertz is the highest, like the higher limit of frequency band for displacement, but not for velocity and acceleration. So at this frequency we will not see any changes for acceleration, RMS and velocity. Okay. And as you can see, at this frequency the peak-to-peak value is more accurate. No, sorry. 9 multiplied by 2 multiplied by 2. It is more accurate, and peak factor is more accurate too, because on low frequencies our vibration exciter has its own specific. Okay, so if we recalculate this value, 8.8 micrometers, keeping in mind our filter, so we are getting 6.2 micrometers, and our sensor says that it is 6.2. Cool. But velocity RMS and acceleration RMS for this frequency doesn't have any like changes, and it is very accurate. as a feedback sensor. So let's move on to 1 kilohertz. At 1 kilohertz, we don't have to see any like changes for acceleration, but for velocity we will have minus 3 decibels, and for displacement we will have like minus 40 decibels. So let's see. And it says that our acceleration measurements are very accurate and very close to our feedback sensor, but velocity measurement has some difference. So let's recalculate it. Okay, and at 1 kilohertz, if we apply a filter coefficient to actual value of our feedback sensor, we are getting 1.55 as at our sensor, 1.55. So I can show you, I will show you a table with these coefficients for third octave frequencies just a little bit later. Okay, let's move on to 3 kilohertz. The same magnitude, 2G, start. Okay. Let's go back to the datasheet. At 3 kilohertz, we will have minus 3 decibels for acceleration and much more for velocity and displacement. So let's check acceleration. Okay, feedback sensor says that it is 13.87 multiplied by 707, and if if we apply the same filter for our feedback sensor, we will get this value, and our sensor has very close measurement to a feedback sensor, so we can calculate the error percentage, for example. So 9 by 8 it is lower than 1% of error at 3 kilohertz. So good job, ETS3D. Okay, let's stop the exciter. So right now I think that you are understanding what is frequency bands and how to understand these values and how to use our datasheet with this very helpful information. So also our sensor has third octave spectrum feature. Let's get it bigger. Sorry. So we have third octave filters in bands from 10 Hz to 10 kHz. Each band has its own width. In this document I have widths for these bands, and as you can see, the highest is average geometric frequency, the wider band it has. So right now I will put some high frequency signal on our vibration exciter. Let's say 6 and 3 kilohertz. And we can put like 10G. And compared to this document, 6 and dot 3 kilohertz frequency lies is the average geometric average frequency for this band. So, and here we can see that in this band we have the highest level of vibration RMS. I forgot to say that in these columns we have RMS of acceleration for one axis. You can change this axis in settings. As you can see, it is much better to understand in which band you have your RMS, your vibration, so you can determine more effectively your problems of your mechanisms or machines. Also, you can change the scale of this figure and change some level, low limit and high limit too. Okay, so our sensor, as it described in datasheet, provides vibration measurements not worse than 5000 Hz. But for this feature, we can provide up to 11.2 kilohertz because our sensor has like a very high sampling frequency, sampling rate. Of course, you are getting some error percentage at these frequencies, but in dynamic you can see some changes of your mechanism, and all these features are you're getting like out of the box. You don't need any additional devices. Just connect to a device and read the registers. Register map will be updated for third octave filters because we are working on it. And let's move on to settings page. Here you can change your connection parameters such as baud rate. Let's change it, for example, for 57,600 baud rate. Also, because our values are represented in float format, float format has its own standard, EE 754. Default byte order is ABCD, but in our software you can change to CDAB, BADC or DCBA byte order. Also, you can choose another axis for third octave filter feature. Okay, let's apply another baud rate. It says that saved. We need to restart device. Okay, let's restart device. We need to reconnect, connect. Okay, success. So I think that this is all I want to say to you today. So thank you for your attention and good luck and goodbye.
Thank you, Vladislav. As I said, this webinar and the first webinar you can find on our website and YouTube channel. In conclusion, I want to tell that this device that was developed to connect to the computer to different USB ports is already developed and can be supplied with the sensor. If you have any questions, please contact me via the contacts from our website. So thanks for your time. Goodbye.